right, our last presentation, our last presenter has the toughest slot of the day. It's the last one before the reception, but from past experience, I know he's more than up to the challenge. Our last presenter is Yair Siegel, Director of Strategic Marketing for CEVA. The title of his talk is Fast Inference in Low Power Systems via CEVA's Deep Neural Network Solution. Yair serves as CEVA's Director of Strategic Marketing, covering business development, OEMs and partnerships, and addressing audio, voice, deep learning, and computer vision applications. So his presentation outlines the challenges of implementing high-precision advanced neural networks for embedded vision, among other things explaining how CEVA's automatic software tools in combination with processing units can assist these challenges. Yair?
Thank you, Brian, and thanks everyone for staying so late in the afternoon to listen to the presentation. So, when I was a young engineer back in the day, we developed tools back then for enabling algorithm developers to take their algorithms which were built for research and taking those into production platforms like mass production, mobile phones, and things like that. Back then in the day, the hot area was modem design, and the tools that we were working on were mostly development tools like compiler and IDE, and so on. It's great that now, after 20 years or so, still the products that we developed back then are now in mass production. So actually, the top two manufacturers today for mobile phones are using our technology from back then in at least part of their production modems today that all of you have in your pockets. So after 20 years, CEVA is still developing a technology that go into mass production, and the hot area today, as we all know, is neural network. And what we've been doing for the last couple of years is developing tools that make life easier for the algorithm developers, the guys that are building the neural networks, to take their research networks and port them into the mass production, into mobile phones or into wearable devices or into automotive. And this is the topic of my presentation, basically explaining what we supply for inferencing to mass production platforms. So I hope by the end of these 2 days, you guys already have a good sense of what is the option to take embedded vision and what type of applications can be used in. So I'm not going to go into deep details here, but I would like to at least explain a few use cases which are interesting and relatively new in the market. So one interesting use case that at least personally I just saw last week in the Facebook conference. So Facebook are actually using Inference to generate semantic segmentation, and they generate a bouquet effect on the mobile phone, essentially using single camera, which is very similar to what you can get today with the iPhone 7 Plus, which is using a dual camera, but is not necessarily using a deep learning solution. So that is very interesting usage of deep learning. A second interesting use case is today more and more of us have huge amount of videos, of images, and so on. And there is a need to be able to find something very quickly in the videos. So top guys that own the video engines like Google and Facebook and so on, they are using deep learning in actual mobile devices and others to find objects and other things very quickly on images, on video, via tags, and so on. So for example, you can search and find all your images in your phone that have a car. However, we cannot go and find all the images or all the videos that can show who is stealing a computer from my house. This is still not there in the market, so there's still a ways to go. Another interesting use case that is in the market today, for example, Samsung in their latest Galaxy S8 is using face and iris recognition in order to increase the authentication quality to unlock the device. Still not fully using deep learning, but deep learning is going to be there quite soon. So if you are going to develop or consider to utilize neural network in a device using inferencing in the near future, there are a few considerations that you might want to look in to put on your device. So first consideration is to look at using neural networks compared to what we call traditional vision. So neural network comes and has some advantages like robustness, like accuracy. However, traditional vision has a better proven track record, and possibly you should consider, at least in the near term, as the neural networks get more accelerated into the mass production, to maybe combine some portions of your algorithm to use neural network, some portions to use computer vision. Another consideration is, do I do the inference on the cloud? Do I do the inference on the edge? Interesting discussion here is just last week Amazon announced their new Echo device called the Echo Look. So essentially they added a camera to the Amazon Echo, and this camera can do things like give advice on fashion and so on. And there was a big discussion in the media regarding the data privacy. So obviously if they're loading all the data to the cloud, it's quite hard to protect. Versus if you're doing this more of the analytics and the AI on the edge device, it's easier to protect the data. You don't necessarily have to load all of it into the cloud. Other considerations like latency and computation power, of course, when you decide what you want to do on the edge, what in the cloud. I think also here there's no clear answer, meaning it depends on the device that you're doing. Maybe in some devices you would want to do more on the edge, others maybe more on the cloud. When we talk about the networks themselves or that we are using, we can look at a nice graph that we have from one of the popular articles for neural network, and see that as the accuracy of the networks improves, also the horsepower that is needed, or the number of ops per frame that are needed, is much higher. So we can compare two popular networks, AlexNet back a few years ago versus YOLO, which is popular network these days. And even though the tiny YOLO is targeted for very light processing, it needs much more horsepower than the AlexNet. On the other hand, if you're going to mass production, you care a lot about battery life, you care a lot about cost, so it won't be expensive. So this is an opposite trend to being just able to run endless amount of compute on the device. So essentially all of these together, they call for efficient engines that can be good horsepower but low energy, and they also call for better networks, meaning networks that will be able to do good accuracy but will use less computation. So when we go and develop our solution for inferencing, we really want to make sure that we have very high performance and we use limited energy consumption. However, we want to be flexible in the solution to enable continued evolution of the deep learning types of networks. So if we look at the recent 2 to 3 years, there has been a lot of evolution, and very quickly. So the layers are changing, the topologies are changing, and so on. So for example, if 2 or 3 years ago we had networks that were doing object detection and they were more linear networks, a year or two ago we had networks that were doing semantic segmentation, but they still had different detection and classification phases. And today networks that are popular like YOLO, they have a single stage for both the identification and classification. So it's very important to have a solution that is flexible and can move on to the next solution, what people will develop, I don't know, in 1 or 2 years. So when we talk about CEVA's solution for inferencing, we call this solution CEVA Deep Neural Network. We basically bolster onto the popular frameworks like Caffe and TensorFlow. So we are not intervening in the training phase itself. We get as an input the trained network, which is typically floating point with weights. We feed that into our offline tool, which essentially is a executable or push button application, and this tool takes the network and converts it automatically to be better suited for embedded for mass production, meaning we convert automatically to fixed point. We adapt it to be more efficient for running inferencing on our platform. And then we can just call the libraries on the processor and do the inferencing like identify dogs. So if we look at CEVA's full vision solution, we do more than just CNN. We also can do vision and others. But the CNN solution, what they call a CDNN toolkit, actually incorporates a combination of software framework, software libraries, and a variety of hardware processing units, both programmable, DSP, and hardware accelerators. And let me explain more about each of these different units now. So you can see here basically our full offering for the CDNN toolkit. As I mentioned, the input of this solution is a trained network, and the output is an optimal network that can run in mass production and low-cost devices under a Vision DSP, and as well as a hardware acceleration unit. So we have a few generations. The latest generation is adding an option for a hardware acceleration. The framework itself supports all of the different generations. It stays very similar to people as they are migrating from one generation to another generation. So if we look at the different components, so we have the hardware accelerator, which is offloading some of the neural network, and I'll explain it in a bit. Then we have the driver for that running on the DSP engine. We have the runtime libraries of basically we pre-optimized all the different layers of the neural network on the DSP. And then we have API to call those layers both on the DSP side as well as the host CPU side. And we have the network generator, which, as I mentioned, is an offline tool which manages all these components and is able to utilize them very efficiently, utilize a combination of different DSPs with a different amount of accelerators as well. So if we look at the processing of the CDNN solution, we mentioned that the neural networks are all the time evolving. However, we've seen that the convolution layers are still dominant even as the evolution is moving of the neural network, but they're really the most demanding layers of the neural network. So what we've done in our solution, we've taken the flexibility of the DSP, and then we're offloaded the convolution layers to a dedicated hardware accelerator. And this way we're able in our latest generation, which we call CEVA XM6 with the CNN accelerator, to achieve up to 12x acceleration in terms of performance capability for the same energy compared to our previous generation, which is called the XM4. And the XM4 is already, these days, it's entering production. We have over 30 design wins. So 2017 is going to be a lot of production devices with the CEVA XM4. And today with our latest generation, we already have a few engagements, customers, and probably they will have devices coming out end of the year or next year. So looking at the hardware components of our CNN solution, as I mentioned, two main units, the XM DSP, so we have the XM4 and the XM6, and then the CNN hardware accelerator. So the CNN hardware accelerator is basically offloading the convolution layer. It has a big convolution unit, up to 512 max. We can support up to 16-bit fixed point precision, and it can also run as a standalone unit on its own. The DSP is executing the rest of the layers that are more changing over time. It can instantiate the hardware accelerator, and we can work with one or multiple accelerators. So it's quite flexible in terms of the devices that it can handle. Let's see a few examples of utilizing CEVA's network. So here we can see an example network that was utilized by one of our partners, DeepGlint. This is a deep learning software company in China who develops neural networks for surveillance. So they took our CDNN solution, and here you can see in these streams basically the bounding boxes of two networks. The first network is the original network which they took in CAFE, which is 32-bit floating point. That's in red, and then in green you can see again the output or the network of running after CDNN, which is 16-bit fixed point. So you see very near accuracy of the network. A second example is a network such as faster RCNN. So if you look at the original network, a quite complex network and utilizing a very high memory bandwidth. However, after running it through our CEVA network generator, we are able to keep bit accuracy, but we generate much lower memory bandwidth. A third example, which is the YOLO network, which is quite popular these days as doing both classification and detection. So if we're going to run YOLO on our CDNN tool, so we need to do a few things. First of all, we need to set up the network generator, tell it how many DSPs we have in the system, how many accelerators, and then we initiate the generator. First stage, the generator will take this code and will port it, as I mentioned, to fixed point implementation. Second stage, it will take the network and it will run it on the different hardware units according to the configuration file. So it's able to balance the performance load between multiple engines. So this is also part of what the network generator is doing. It is able to combine the different layers from the original network to save on memory bandwidth. So if we look at the example performance using YOLO on our solution, so if it's running only on the standalone DSPs, we're able to achieve tens of frames per second in real time on the device of a tiny YOLO network. Versus if we add hardware acceleration, we're able to achieve a few hundreds of frames per second, which is definitely a magnitude more in terms of horsepower. Okay, so summarizing it all up, so the CEVA deep neural network, we basically have a lot of market recognition. As I mentioned, we already have dozens of customers working on different products. We just won an award from China Electronic Market, the Editor's Choice Award. It is actually second generation already in the market, so we're close to 2 years already utilizing this network with customers, with partners. So, we're all the time improving. We have, of course, in addition to the major releases, we have some improvements ongoing all the time. We do support the main frameworks for deep learning, which are Caffe and TensorFlow. We support variety of networks, variety of topologies, and basically all the important layers in these frameworks. And we also support networks that have variable sizes ROI, so this is a part of the solution. All of this is basically done by what we call a push button conversion. So we take the pre-trained networks and port them very quickly to our platform. And of course, we enable running these deep learning and AI into mass production devices such as mobile phones and other devices. All in all, the solution is really working together with and optimized for CEVA's Vision DSP as well as CEVA's CNN accelerator. So it's not only software, it works tightly with the hardware modules. And basically, if you're interested in more information, we actually have a booth right in the entrance to the Expo, and happy to show you some of the live demos like AlexNet, GoogleNet, YOLO, and others running on our devices. So that's all. Thank you.
Nice job, Yair. Thank you. Comments or questions from the audience? I have one question. So when did you first announce CDNN?
It was, I think, in October 2015.
Okay, so less than 2 years ago, right?
Right.
You're already in version 2 of CDNN. Facebook just announced Caffe 2, right? There's evolution of frameworks and revolution of new frameworks and networks. What's your plan for keeping your software tools up to date as this evolution continues?
Right. So first of all, it's great to see big companies like Facebook support neural network. Not only that, they're actually taking like Caffe and saying, okay, CDNN2, it's all about getting more out of the framework and targeting it for mass production like mobile. So it's great. Unfortunately or fortunately, our engineering is so overloaded with actual customers for products, so we haven't been able to support that yet. But we release new versions all the time, so I'm sure this is something that once we see enough interest for the market, this will be part of our roadmap.
Okay, great. I knew you'd have more questions. Go ahead.
So if your software converts the network from the floating point to a fixed point, how do you validate the accuracy doesn't drop too much? I mean, what's the flow is like?
Right. So first of all, this is something that we have confidence in that, and we have dozens of customers and lots of partners, and we run our own tests. But we guys like Deep Glint and others that some of them are public, some of them are not public. They see very very good accuracy in that. So there is some drop, but usually it's within 1% versus the original floating point network.
So, for example, if I have my specific network, not public ones, so if I give you my network and you do the conversion, so I also need to provide the test data to verify how much the accuracy drop, what's the flow is like.
No, you can. Each network has its own. It's like asking a question: How do you know that your network is accurate at all, right? So the same test bench that you're running on your network, you can run it after the generator, and there's no difference in terms of that, and you can validate it's working quite well. So we have done probably hundreds of networks by now, and we continue to work with many, and we don't. Our tool is very robust. If there is an issue, not 100%, we can always work on improving, but we see very high accuracy compared to the original networks.
Thank you. Another question?
Hi. In your YOLO example, so you said that you are automatically partition it and balance it across multiple hardware accelerator. So does it include any third-party accelerator other than Cadence, DSP? That's my first question. And second question, when you balance it, I mean, how do you balance it? Of course, how do you determine what kind of computing element you have, and then how do you balance those kind of layers and workloads?
Okay, so for your first question, so yeah, we support different number of units because we are doing a product that goes across many different markets, many different devices. So different customers need different number of units. We do have already a variety of customers that also have their accelerators. In some cases, they want to adapt our tool. In some cases, they have their own tools. We can run only portions of the library, or some of the layers in our processors, so we enable what you're asking, but it needs to be discussed specifically. The standard tool is not, it does not support any third-party accelerator automatically. It's work that needs to be done either by CEVA or by the chip vendor or whoever is working on it. So, it's not out of the box. And what was your second question? Can you repeat?
No, actually, I think you covered the second question. My question was, how do you balance it across the different computing elements? How do you know what kind of computing element you have there? And
right, so if you build a tool, you know the capabilities of that accelerator, so you know to balance it accordingly, right?
Any other questions? You are free to go. All right, thank you very much.